All right. Hello, everyone. This is the last part of this chapter, part 6. So we are going to go over two more problems of this chapter. This is going to be a shorter lecture. So we're going to do problem 6.121. Here, take some time. If you want, pause the video and read through the question to understand it. So consider a Carnot heat engine. So it means that we are considering an ideal or reversible cycle heat engine. It's heat engine, so it receives heat, generates work. Executed in a closed system as shown. It's a closed system using given amount of steam as the working fluid. So this is like a custom design heat engine. This may not exist in reality. This is not a power plant. This is not an internal combustion engine. This is like a kind of experimental or theoretical heat engine. So it may not be an actual device in real world. So it is known that the maximum absolute temperature in the cycle, in this theoretical cycle, the maximum absolute temperature in the cycle is twice the minimum absolute temperature. So what does it mean? It means that TH, which is the maximum temperature, is twice TL, the minimum temperature, both in Kelvin. And the network output of the cycle is 25 kilojoules. So it receives heat, generates work. The work output is 25 kilojoules. If the steam changes from saturated vapor at the initial state to saturated liquid during heat rejection, so when it's rejecting heat to the surrounding, the steam changes from saturated vapor on the right side of the dome to saturated liquid on the left side of the dome, PV diagram or TV diagram. So this happens during heat rejection. So it means that during heat rejection, the steam in the heat engine, the saturated steam is converted to saturated liquid. Determine the temperature of the steam during the heat rejection process. So then it means that since we do have a phase change process from saturated steam or saturated vapor to saturated liquid, the temperature doesn't change during this process because it's a phase change process. So based on the given information, we need to find the temperature during the heat rejection. All right, so you may want to pause it, read it once or twice again. Okay, so the assumptions that we need to make here is that the engine is set to operate on a Carnot cycle. So we can now go ahead and take advantage of the equations for a Carnot heat engine, which is totally reversible. So for a Carnot cycle, the efficiency is given as 1 minus TL over TH. The problem mentioned that actually TH is twice TL. So TL over TH is equal to 1/2. So the efficiency, the thermal efficiency of the cycle is 0.5, 1/2. Okay, that's good because now we can go ahead and use this efficiency in order to find QH. The problem mentions that the total work output from the cycle is given. It's 25 kilojoules during the time period. It's not a steady flow process. It does have a duration like delta T. So with W given and eta thermal found, we can go ahead and calculate QH. This QH is the heat given to steam from the high temperature reservoir. Then, however, the problem is focused on heat rejection process, not heat addition. So therefore, we can go ahead and by writing an energy balance, the first law for the entire heat engine, we know that QL is equal to QH minus W. QL is energy out, W is energy out. The sum of these two is equal to QH, which is energy in. So QL is therefore equal to 25 kilojoules. Okay. Now, if we divide it by the total mass of the steam in the heat engine, so this is our heat engine, it is like a closed system. But its volume changes, so it's a piston cylinder. So based on this, lowercase q, QL is equal to the total QL divided by the mass. So we have found this QL. The problem states that the heat rejection process actually occurs based on some given conditions. So it occurs as like in the form as like steam in the saturated form is totally converted to saturated liquid. So it is like we move on the dome. So if I want to draw it here, I do not have the right tools, but let me try. If I draw the PV or TV diagram, so that would be the dome. So the problem states that QL heat rejection process starts from here on the right, it's saturated steam, and on a horizontal straight line it rejects heat until it reaches this final point. So that's the heat rejection process, QL. So heat per unit mass. Okay. So what does it mean? So you remember from previous chapters that this QL is this is actually the heat of vaporization, right? This is the heat of vaporization, QL, because we are moving from the saturated vapor branch to the saturated liquid branch. So this QL is therefore equal to Hg, which is the enthalpy here on the right side, minus HF. Therefore, QL is simply equal to HFG. So now the problem wants us to find the temperature associated with this process. So let's say if this is a TV diagram, temperature versus a specific volume. So what's the temperature associated with this? Okay, so we do need to go to the saturated tables in terms of the temperature and look at HFG for different HFGs associated with different temperatures, and see that for what temperature that we are looking for, HFG is equal to 2427.2. Well, most probably we do need to go ahead and do an interpolation because it's unlikely that we can find this exact number in the table. So probably we do need to do interpolation. Okay. So I have the interpolation process in the next slide, so I cannot go back and forth. So now let's go to the table. Again, we do need to look at the table, look at the HFG associated with different temperatures and see at what temperature HFG associated with that temperature is equal to this number. If it's not equal, then we would need to do interpolation. So here's the answer, but we will actually find it in the next slide, 31.3. All right, so this is the saturated water temperature base. because we want to find the temperature associated with heat rejection. If you look at the table, you see that our HFG, which I forgot its exact value, is actually between these two HFGs listed in the table. That number is between 2417 and 2429. But that's somewhere in between, right? So for each of these HFGs, we do have a temperature, one associated with 30 degrees C, the other one 35 degrees C. So we just need to do a linear interpolation, put that other HFG given here, and find the associated temperature. That temperature will become 31.3, which was found in the previous, which was listed in the previous slide. So here I haven't shown the detail of linear interpolation. We have done it multiple times in the class. So simply you do have, for your line, you do have 2 points. One point is the coordinates of one of the points is 30 and this HFG. The coordinate of the second point is 35 degrees C and this value of HFG. Then you can pass a line, and then for the point of interest, you do have its HFG here. You can go ahead and find the corresponding temperature. That's the concept of linear interpolation. Okay, so that's it. So you see that in this chapter, in this particular question, so we did have a heat engine. It was operating in a Carnot cycle. But in order to do the problem, we need to go back and use our knowledge from previous chapters. And we need to go ahead and use the property tables. So all of these chapters are interconnected. In order to be successful in this chapter, the prerequisite is that you already have learned the materials of the previous chapters. All right, so now let's do the last problem of this chapter that I'm going to talk about. Well, unfortunately, the schematic has been covered by my video, but we do have it in the next slide as well, so no worries. So a heat pump. So we do have a heat pump. It pumps heat from like outside of the house, from the window, from the surrounding to the house, with a given COP of 2.4. So this heat pipe is used to heat a house. It's like in the winter in not so cold areas. So that could, for instance, work well in Texas, let's say. When running, the heat pump consumes 8 kilowatts of electric power. So that's the power input to the heat pipe. That's the power required in the compressor, required by the compressor in order to compress the refrigerant. If the house is losing heat to the outside at an average rate of 40,000 kilojoules per hour, so the house itself is losing heat to the surrounding, because even though the house is insulated, the insulation is not perfect. Still, heat can transfer through the walls, so we do have some heat loss. So there's no way to have like a perfect insulated house. So during the process, this amount of energy is lost per hour. The power here is kilowatts is per second, but this value is per hour. So we need to convert it to per second so that everything be consistent. So, and the temperature of the house initially is 3 degrees C. So let's say someone has gone to work and is coming back home in the evening, wants to turn on the heat pump, and the temperature in the inside is 3 degrees C when the heat pump is turned on. Determine how long it will take for the temperature in the house to rise to the comfort level 22 degrees C. 22 degrees C is equivalent to about like 75 degrees F. So assume the house is well sealed, it is not well insulated, because we do have heat loss, but it is well sealed, so there is no air leaks. So air cannot leak, but heat can leak. And take the entire mass within the house, the air, furniture, etc., mostly like air, to be equivalent to 2,000 kilogram of air. Okay, so the equivalent mass is 2,000 kilograms of air. So it means that you only consider air in the house, and the temperature of the air must increase from 3 degrees C to 22 degrees C as you turn on the heat pump. So what are we supposed to determine? Determine how long it will take for the temperature in the house to rise to 22 degrees C. So you may want to go ahead and pause the video for a minute and read through the question again, and then come back for the solution in the next slide. Okay, we sort of have the schematic here. So we do have a heat pump at the bottom. So QL, which is covered here. So QL is added, is extracted from the surrounding. And then the compressor work is used to transfer this QL from the surrounding. So QL plus W dot of the compressor becomes Q dot H, which is provided to the house. So, all right, so first of all, this is for the 1,000 kilojoules per hour. This is the heat loss. So if we go ahead and convert it to kilojoules per second, because this is given in kilojoules per hour. So divide 40,000 by 33,600 seconds, it will become 11.11 kilojoules per second or kilowatts. Okay, fine. That's the heat loss. So based on the given information, the COP is given. So one assumption here is that we assume that the COP of the heat pump remains constant during the operation, because the COP may actually change during the initial startup. The COP may be different from the steady operation, but here we assume that COP is constant. We also assume that air, so I forgot to mention the assumptions at the beginning, sorry about that. So we assume that air is an ideal gas, because as you remember, we said that the temperature of the air is supposed to increase from 3 degrees to 22 degrees C. So we could either use the air tables for this temperature increase, how much energy, how much heat is needed for this temperature increase. We could either use a specific heat, average specific heat, or we could use the air table. So here we're going to use this average specific heat. And we also assume that the house is well sealed, so air cannot leak through the windows, under the door, and so on. All right, so now back to the problem. So for this constant specific heats, so we know that the volume of the house is constant, therefore we can go ahead and find CV. And it depends whether we want to use delta U or delta H. So it will turn out that we do need to use delta U, because the air is confined in the house. So we will see that actually delta U has to be calculated. So we do need CV to calculate delta U. So this CV is obtained from table A2 with this average amount. We found it at room temperature, because the temperature changes from 3 degrees C to 22. We can, if the tables allow, we can find this. We can find CV at average of 3 degrees C and 22 degrees C. Or we can just go ahead and find CV at the room temperature. The difference will not be much. So this is an assumption that has to be mentioned. All right, so we found Q dot loss through the walls, and since COP is given 2.4 and also the work required by the compressor is given 8 kilowatts, we can go ahead and find Q dot H. So this Q dot H, which is also shown here, this is the heat provided to the house by this heat pump system. 19.2 of kilowatts is given to the house. So, however, 11.11 kilowatts of this heat is actually wasted. So 19.2 is given to the house, 11.11 is missing, per second is just missing because of the because of the heat loss to the surrounding. So now the question is how to calculate the amount of the time required for this heat pump to bring the temperature from 3 degrees C to 22 degrees C. Okay, so this is a very good question, by the way. So we need to consider the air in the house as our system. So this would be our heat system now. So if we write the first law of thermodynamics on this system, energy in minus energy out is equal to delta E. So this is not a steady flow system. This is like a constant volume, constant mass closed system. So energy in minus energy out is equal to delta E. So if we neglect the kinetic energy and potential energy, which is justified, so this delta E is actually equal to delta U. So delta U here, change of the internal energy. So energy in minus energy out. Energy in is equal to QH, which is given to the house by the heat pump. So this Q in is the Q of the heat pump. Q out is this Q loss. So this here is per unit time, but here we don't have unit time, so we need to take that into account. So this Qn is the heat given to the house by the heat pump. Q out is the Q loss. The change between these two is equal to the change in the energy or internal energy of the system, which is the air in the house. It's equal to delta U, or delta U is equal to mCV delta T. This is an ideal gas, so delta U for an ideal gas, change in the internal energy, is CV delta T. So based on this, we know that for air, we do actually need CV, that we found it from table A2. We don't need CP. Here we do need CV because we want to find delta U. If here we had delta H, then we would need to use CP. All right. So here, this is the total amount of the Q coming in and Q going out through the walls. But here we do have the heat rate. So if we multiply this Q dots by delta T, the duration, the time duration of this process, then we will get this Q dot in minus Q dot out times delta T. And this delta T is the amount of the time which is needed for the heat pump to bring the temperature up from 3 degrees C to 22 degrees C. And this is equal to mCV delta T. So we do have this Q dot in, which is 19.2, Q dot out, which is the heat loss. So we do have the mass of the air, which is given 2000. We do have CV, and we do have delta T. So here the temperature is in degrees C. So generally you should use the temperatures in Kelvin, but since this is temperature difference, it doesn't matter whether you convert them to Kelvin or directly write them in degrees C, because that's the difference. Temperature difference in Celsius or centigrade is the same as temperature difference in Kelvin. Okay, so everything is known here. So if you do the math, the calculation, delta T is equal to this amount in seconds. So directly what you find using SI units, the unit for the time will be in seconds, and then you can convert it to hours if it's needed. So this is like about 0.9 hours. So it takes about 1 hour for the heat pump to bring the temperature from 3 degrees C to 22 degrees C. So that's it. So one question that I could ask here, 1% type of questions that I used to ask in the class. So here's one question. So what happens after this 0.937 hours? So if the heat pump continues to run at the same capacity, then what will happen? Because it already has reached the 22 degrees C. So if the heat pump continues to run at the same pace and the same rate, the temperature in the room will continue to increase from 22 degrees C to higher temperatures. So in order to prevent that, because we don't want the room to become too warm, too hot, then we would need to go ahead and turn down the heat pump so that it generates, it provides heat at a lower rate, at a rate which would be equal to how much? So once we have already reached 22 degrees C, then we would need to only provide 11.11 kilowatts of heat to the room, equal to the amount of the heat which is lost to the surrounding. Okay, so that's it. So this brings us to the end of chapter 6. So we went over the content of this chapter, the Carnot cycle for the heat engines, and then we talked about heat pumps and refrigerators and the associated reverse Carnot cycle. We did some sample problems. So as you see, the equations for this chapter, we do have just very limited number of equations. However, when it's combined with the materials of the previous chapters, so here you see we actually use the first law for a closed system. So it is not independent. So this chapter is sort of easier to handle, but the materials are dependent on the previous chapters as well. So you need to actually make sure that you have understood the materials of the previous chapters very well in order to be able to handle this chapter. All right, thank you very much for your attention.